Yes, students, let us discuss tendency of lanthanoids to form complexes. Before to begin this topic, I want to make clear the concept what is meant by complex. Complex is a compound between Lewis acid and Lewis base. Lewis acid accepts lone pair of electrons and Lewis base can give lone pair of electrons. So there is a mutual sharing of lone pair of electrons in coordination compounds, and such compounds are called complexes. D block element or transition series elements, when you have studied at that time, you learn they have extensive tendency to form complexes. They are excellent in formation of complexes. Then what is the criteria to form complexes? Complex is a reaction between metal and surrounding that we say as ligand. So metal needs to fulfill some properties and ligands also accordingly. Let us talk about metal first. Metal attracts, gathers, takes attention of the ligands. To take that attention, in order to have the crowding of donors, metal should be with one quality. And that quality is, it should be with sufficient charge, positive charge. Then it will attract the ligands. But only mere quantitative charge is not important. It should be with sufficient charge density. Means tripositive charge is there. Tripositive is a considerably high charge. Tripositive charge is there, but metal ion is big. Then that tripositiveness will be dispersed, will be distributed. Overall density of charge, yes, I am talking about charge density, will be less. So if charge density is less, power of metal to attract the ligand will be less. So that power of metal determines the tendency to form complexes. And transition series elements were with that good tendency to attract the ligands. By the same time, what is the nature of metal ion in the sense of electropositivity, in the sense of HSAB concept, hard and soft, acids and bases? That also is important one. These lanthanoids which we are studying, they come in which category and which kinds of ligands they will attract, that also we will discuss. So what is meant by complex? Complex is a coordination compound between metal ion and ligand. Now come to the actual lanthanoids. It is found the tendency of lanthanoids to form coordination compounds is poor, moderate tendencies there. Compared with whom? Compared with transition series elements. Compared with lower actinoids. They have good tendency, and these lanthanoids have comparatively less tendency to form complexes. Now question arises, why it is so? It is because just now I said one term. What is that term? Charge density. Charge density of lanthanoids is less, is poor, and therefore they fetch the attraction of the ligand to less extent, and therefore the bond strength is what? Less. Number one. Secondly, while formation of the compounds, very outer orbitals are made available, because in ionic state there is no electron in 6s orbital, there is no electron in 5d orbital, but electrons are there in 5s and 5p. So outer orbitals are available. So only just the electrostatic force of attraction is there between, electrostatic force of attraction, because of that crowding initiates. So ligand can take a outer space to accommodate their electron. Sufficient orbitals are there because whole outer orbitals are for what, the ligands. But attraction will be somewhat less because charge density itself is less. No? Why charge density is less? Because size of lanthanoids is larger. Why size is larger? They are at lower period. Lanthanoids are at 6th period. So as we go down, size increases. So because of the increase in size, but charge is what? Tripositive. Very few times tetrapositive. So charge density is less, and due to which attraction is less, and therefore my first point is lanthanoids have poor tendency to form coordination compounds or complexes in comparison to transition elements and lower actinoids. It is because of larger size of lanthanoids. And this point, that's a point number 2, I divide into sub points. In that first sub point, tetrapositive lanthanoids have more tendency to form complexes. Tetrapositive lanthanoids form somewhat more stable compared to tripositive lanthanoids, compared to dipositive lanthanoids. So stability. So what is the sub point of second? Stability of complexes decreases as charge decreases. Tetrapositive lanthanoids are more stable than tripositive and then dipositive lanthanoids. Why it may be? Because if lower is the charge, lower will be the charge density. Lower the charge density, lower will be the attraction. Lower the attraction, less will be the stability. So stability or tendency, formation tendency, that we are discussing. Now second sub point of this point number 2. If we study lanthanoids, lanthanoids are from lanthanum to lutetium. As we move from lanthanum ion, say lanthanum plus 3 to lutetium plus 3, size decreases. So what do you think? Smaller the size, more powerful that cation will be, more powerful that anion will be, or will be weaker? Yes, it will be smaller. So tendency to form complexes increases with increase in atomic number. Lutetium plus 3 forms strong, stable complexes compared to lanthanum plus 3. So this second point was related to stabilities of complexes of lanthanoids. Now point number 3. About metal ion we did discussion. Now these metal ions, these lanthanoids, generally we represent Ln plus 3, combines with which ligand so that stable complexes are obtained? For that you need to understand HSAB principle, hard and soft, acid and base principle, more precisely Pearson's principle. Lanthanoids are hard acids. If these are the hard acids as per Pearson's principle, with whom stable compounds will be there? Hard bases. So ligands should be hard bases. Ligand should possess such a donor which is hard one. Ligand should possess more electronegative donor. Ligand should possess donors like fluoride, donors like oxide, donors like nitrogen, which are more electronegative. So ligand possessing donor atoms like fluorine, chlorine, nitrogen, oxygen, those only can form bonding with these hard acids, means lanthanoids. So what is our point number 3? Lanthanids form stable complexes with those ligands which have donor atoms like oxygen, fluorine, chlorine, means more electronegative. For example, oxalate ion, oxalate anion. So two oxygens who have each have one negative charge, those will be the donors, so it can form chelate. Second example, EDTA, ethylene diamine tetraacetate ion. 4 negative charges are there. 4 oxygens bearing those negative charges and 2 nitrogens of ethylene diamine. Total 6 will be the donors, suitable donors. Next, nitrate ion. Nitrate ion, out of those 3, 2 oxygens will be what? The donor. Chloride also can consider, fluoride also can consider as donors. So such ligand can form coordination compounds. It was our point number 3. Now point number 4. Again we are discussing about ligands. Now ligands are approaching towards metal ion. So how many ligands can surround the metal ion? How many bonds are possible with the metal ion? That is called as coordination number. So that coordination number is decided by 2 means. Number 1, metal ion, because metal ion is giving the platform to the ligands, no? So what is the size of the metal ion? How much space is available around the metal ion? Accordingly, number of ligands will be there. By the way, number cannot be decided on the basis of space, because ligand also has their own space. Ligands also have their own sizes. So if bulgier ligands are there, then few ligands will be there. If smaller ligands are there, large number of ligands can coordinate, large number of ligands can surround. So both size of the metal ion and size of the ligand, steric arrangements of the ligand affect the coordination number. Now let us see one example. Fluoro complex. Fluoride is a small anion. Compared to other halide ions, fluoride is a small one. So small, then more number should be there. But a lanthanum complex I am discussing. Lanthanum has charge +3. So for +3, how many fluorides? More can possible over there, but minimum 3 should be there. So those 3 fluorides are considered. 3 fluorides and remaining water molecules, because I am considering the formation of this complex in the aqueous medium. What is found? 11 is a coordination number, means 3 fluoride and 8 water molecules are surrounding, causing coordination number 11. Because of small size of fluoride, 11 number is what possible. Now let us take little larger halide. After fluoride, who comes down in halogen series? Chloride. Yes, chloride is larger. So what do we expect? If I take chloride, then the coordination number will decrease or increase? Yes, will decrease. So let us see what is the coordination number. LaCl3 and number of water molecules are 6. Means what is the coordination number? 6 oxygens from the water and 3 chlorides, chloroligands. So 6 plus 3, 9. So coordination number is 9. Coordination number decrease. So here, what is the conclusion? Size of the ligand affects the coordination number. Let us understand this by one more halide. Below chloride, who is there? Bromide. Below bromide, iodide. I take somewhat larger halide. If I take iodide, what do you think? Iodide will occupy its own space. It needs more space. So number of iodides, number of total overall ligands surrounding the metal ion will increase or decrease. Now in case of iodide, will decrease from 11 for fluoride, decrease to 9 for chloride. Now for iodide, it further decreases to 6. So what is the formula for the complex? LaI3H2O thrice. So 3 oxygens from the water constitute 3 bonds and 3 iodide constitute 3 bonds, total 6 bonds, total 6 coordination. So coordination number is 6 for iodo complex. So from these 3 examples, it is now sure size of the ligands affects the coordination number, or coordination number depends upon size of the ligands. Now let us study similar complex for metline. So I take example of fluoro complex. So fluoro complex for lanthanum we discuss. Fluoro complex for La+3 we have discussed. Now let us discuss fluoro complexes for Lu, lutetium. What do you think? Who is larger, La+3 or Lu+3? Right, La+3 is larger. Larger metline, more ligands can surround. 11 were the ligands. Now lutetium+3 is smaller. So smaller lutetium+3 will surround less number of ligands. And here number of ligands total are 9. So what is the formula for the complex? LuF3H2O6. Coordination number is 9. So coordination number decreases if size of the metal ion decreases. It is a conclusion from this point number 4. So both metal ion and ligand decides what should be coordination number. Point number 5. What actually the coordination numbers are there? Suppose if I fix the ligand, say water, aqua as a ligand, then how many water molecules can surround for lanthanum+3 and how many can surround for last element lutetium+3? How the coordination number is varying, that we need to discuss. Yes, I told you already, among these lanthanum+3 and lutetium+3, starting element and end element, who is larger? Lanthanum+3. So number of water molecules who can surround will be more. Yes, lanthanum+3, it was found 9 water molecules can surround. So what is the coordination number? Generally, what is the coordination number for lanthanoids? Few followers after the lanthanum, up to samarium+3. The coordination number was found to be majoritically 9. It is due to their relatively larger sizes. And last element, lutetium, which is the smallest one. So lutetium, and in reverse order, if I come to dysprosium. So from dysprosium to lutetium, coordination number is less compared to this. What was here? 9. Now what will be here? 8. It is found 8. And in between few elements are there. Which elements I had not considered? Just I repeat. Lanthanum to samarium I consider. Lanthanum+3 to samarium+3 I considered. And here dysprosium+3 to lutetium+3. So between samarium and dysprosium, who are there? Yes, europium is there, gadolinium is there, terbium is there. All those tripositive ions can show 8 or 9. They are flexible. It is general point of view. For water molecule, if we are to compare, in order to understand the variation of coordination number with respect to the metal ions, keeping a one ligand constant, this point number 5 is there. What point number 5 says? For lower lanthanoids from lanthanum+3 to samarium+3, coordination number generally found as 9, and for higher lanthanoids from dysprosium+3 to lutetium+3, coordination number was found to be 8. It is in general way. Now let us discuss, if we consider few coordination number, what will be their geometry. As I said, 9 and 8 are the favorable coordination numbers for the lanthanoids. If coordination number is 9, geometry is tricapped, trigonal, prismatic arrangement. And if coordination number 8, then geometry is square, anti-prismatic. Okay, it is easy for us to say coordination number 8, 9, 11 or 10. But question arises, how scientists have come across this is a coordination number for this complex? It was a very tough task for the lanthanoids. Students, in 1965, actually breakthrough has taken place about the concept of coordination number and geometries of the complexes of lanthanoids. What happened in 1965? The X-ray diffraction studies revealed the coordination number. Two complexes were studied. EDTA complexes were studied. It is found for lanthanum, EDTA and water shows coordination number 9. And other EDTA ligand was considered where out of 4 acid species, 3 were ionized, 1 was unionized. So protonated previous EDTA you can consider and water molecules. Coordination number was found to be 10. X-ray diffraction study of these complexes give an insight about coordination number of the complexes. Generally 8 and 9 coordination numbers are observed, that we discuss. How coordination number is determined, that we discuss. To where this coordination number is extendable, what is the maximum possible coordination number. 12 is the maximum coordination number possible for lanthanoid complexes, especially the ligands which needs a small space. 12 bonds may possible. For example, CeNO3 6. NO3 minus, but NO3 minus is a binding ligand. So each ligand forms 2 bonds. Such 6 ligands are there. So how many bonds are there? 12. So what is the coordination number? 12. So such a large coordination number possible. And if coordination number is 12, geometry for that complex is icosahedron. Point number 9. From coordination number 2 to 12, such a wide range of coordination number though is possible for lanthanoids, generally coordination number 8 and 9 are preferred. Now further explanation, this coordination number geometry depends upon the ligands which have the attraction with the metal ion. Because of the electrostatic force of attraction between positive metal ion and negative point charge of the ligand, there was a attraction. Ligands were around the metal ion and their arrangement especially depends upon the ligands and size of the metal ion, not on the crystal field effect. And what is important thing, in case of lanthanoids, for f orbital, characteristic orbital, those are well inside, those are buried inside. Outside 5s orbital, electrons are there. 5p orbital, electrons are there. So from surrounding, from disturbance of the surrounding, 4f orbitals are protected, 4f orbitals are shielded, and due to that the more splitting in the 4f orbital is not observed. So whatever number, whoever may be the ligand, 4f orbitals are not disturbed. So due to that, spectroscopic and magnetic properties of lanthanoids do not depend upon surrounding, do not depend on ligand or number of ligand, means coordination number. Though I said lanthanoids have poor tendency to form complexes, but within lanthanoids, among lanthanoids, within neighbors, there is a considerable difference in their tendency. And due to this difference, we got success to separate the lanthanoids. So this tendency of lanthanoids to form complexes, or more correctly, difference in the tendency of neighboring lanthanoids, is successfully used to separate the lanthanoids. Now in next part we are going to discuss lanthanoid contraction, what it is, why it is, what are its consequences.